Good evening, everyone. Thanks for joining us tonight for this very special evening. For those of you who don't know me, my name is Peggy Johnson. I'm here at Qualcomm for 22 years. And I just want to tell you, who laughed over there? Was that you? I heard you. I want to tell you a little story about how I got here. I grew up, as some of you may know, with 14 brothers and sisters. And when it came to college options, really public school was my only option because my parents had a rule: you must go to college and you must pay for it yourself. And I had a third one, which I wanted to be a little bit away from home. And since I grew up in LA, I chose San Diego. And that was my initial introduction to San Diego. And when I first came down here, I was a business major. And I had a job, because I had to put myself through school. And I was delivering mail on campus. And one day I was delivering mail to the engineering department. And the ladies, the two administrative assistants there, thought I was there to sign up to be an engineering major. And they were so excited to see a woman come down the end of that hallway. And I said, no, I'm sorry, I'm just delivering the mail, but tell me about this engineering thing. And I sat down and they talked me into changing my degree to engineering. And on that day, I switched over. And San Diego State has been such a big part of the trajectory of my career. And I'm so thankful. When I did graduate in 4-ish years. It took me a little bit longer. But when I did graduate, my first job was an internship with General Electric. And that turned into really the first part of my career. And at one point, it looked like they were going to pick up and move back east, and I wanted to stay out here. And I simply answered an ad for Qualcomm, but it was the initial introduction to GE that got me into the job at Qualcomm, and that started my career here. But not only has it been obviously very good to me career-wise, San Diego State, but it also introduced me to my husband, who's right here, Eric Johnson. And on my very last day of school, or I guess it was about a month before I was getting ready to graduate, I learned I was 1 unit short. And I had to take one more unit. That's like a heart-stopping thing. What? 1 more unit? And so they said, you can graduate, but you have to take the unit in the summertime right away, or else your degree is no good. So I thought, oh, great. So I signed up for this one last unit, and Eric was teaching the class. And so that's how I met him, and I'll let him take it from here. So thank you again for joining us.
All right, thank you, Peggy. Back in 1986, Fred was my advisor when I was working on my master's degree at State. The education I received, especially in DSP and communications back then, proved to be very valuable for my career. And Fred's been advising many San Diego State students. I suspect some are here in the audience today. Fred has been advising and teaching students for 44 years now, which I think some people here are not that old even. Like Peg, I was somewhat financially challenged at State, and I don't even know if Fred remembers this, but he arranged to have my master's thesis sponsored by an industry partner. He doesn't realize how much that helped me, that little bit of supplement to my income, because my only other income was teaching at 430 Lab back then. Anyway, Peggy and I have decided it's time for us to give back. So in honor of Fred's exceptional contribution to industry and education, we've established a Fred Harris Teaching Excellence Scholarship. Just last week, the first scholarship was awarded to a senior who's presently attending San Diego State in the engineering department. And our hope is you'll join us in honoring Fred by contributing to this fund. Eventually, this fund will convert to the Fred Harris Faculty Fellowship to ensure that San Diego State, in times of budget cuts, will continue to provide quality education to electrical engineers, meeting the needs of Qualcomm and others. Some in the audience today have already donated, and I thank you. And now please join me in welcoming Dr. Fred Harris to the stage.
Thank you, Eric. What was the funding source? Remind me.
Wiltron.
Wiltron. Oh, I remember that. Yeah, Wiltron is now owned by a Japanese company. They're, I can't remember the name of it. Embarrassing. In Mitsu. That's right. Thank you. All right. Thank everyone for coming. It'd be very embarrassing if we had a gathering, I was the only one up here. So I appreciate your being here. I appreciate your interacting with me in my professional career, my academic career. And one of the nicest things that happens when you launch a student out there, they become successful. And it's like a parent saying, one of my kids made it. And here a couple of my kids have made it. All right, so this is a little bug walking around across here. That's in honor of my wife, who has a ladies group called the Ladybugs. So I always get little ladybugs somehow involved in presentations. This talk will be partly humorous, partly informational, and partly technical, because I know some of us do have technical interests and backgrounds. Let's see if this works. An IEEE fellow. Someone called me once when I got my fellow and sang the song to me. And I said, why are you singing this song? I hadn't heard about it. I had received a fellow. So I thought, I'll use that somewhere, so I just did. All right, so I want to thank people who have contributed to today's activity. Of course, Eric and Peggy, David Hayhurst, Corey Kaufman, students, past, present, fellow workers and friends, and of course, Penny Harris first and last, because she's my sweetheart. All right, this is a comment. In preparing this, I realized I spent a lot of time preparing PowerPoint presentations. And this is the one we're doing now. And these are some future travel we intend to do shortly to conferences at different places. And two of my graduate students remind me there are some papers missing from this list, for which they're co-authors, and I'll acknowledge their contribution, but there are missing papers. Now, this is a comment that I heard Penny make to someone once, so I've got to show you her sense of humor. Fred is traveling again. While he's out of town, I'm having the bedroom redecorated. I'm changing it to look like the Marriott hotel room. When he gets back, he'll feel right at home. She was only half joking, you recognize. This is some of our faculty who are in my department, who are in signal processing and comms. And some of them are here. Madhu is here. Let's see, who's here? Amir is one of our newest faculty members. Who else is here? I apologize. Okay. Well, I'm glad you're here. Thank you. So these are bright people, and some of us smile and some of us don't, you'll notice. Now, this is our dean. And I've always wondered how our dean managed to be in two places at the same time. Well, now we know. He's got a clone. We just haven't met the clone. This is me going to work on my trusty steed, Trigger. This is actually in Australia. Australia has the largest herd of camels in the world. And I was at a place in the middle of Australia called Alice Springs. No one knows where Alice Springs is unless you're in Australia. And they had these camel farms, so I took a ride on a camel. This is my other trusty steed, Big Girl. And you can't see it, but that's Penny right behind me, holding on for dear life, as I was holding on for dear life. Riding on an elephant is not a very comfortable way to get around town. We were walking down the street, the elephant was walking by, we were snapping pictures, and the guy yelled down, do you want to ride? Of course you want to ride. So we got up there, and I thought, gee, too bad I'm not down there, I could take our picture. But someone at the conference recognized me and took the picture and sent it to us. And this is, someone has made a comment or two recently, commuting along the 4th floor hallway by the Skateboard Express. Be careful, you can get hurt on that thing. So in fact, one of the people here reminded me that I used to come to class with a skateboard and sit down as if I were a student. And then when we waited to the appropriate amount of time, I would get up and go in front of the classroom, and the student would say, sit down, the teacher's going to come in soon. So it was an interesting way to sneak in on the class. I was raised in New York, and you may recognize, I took this out of a flight, flying out of the window, flying into LaGuardia. It was just a neat picture. And there's Manhattan and Brooklyn, and a bridge, and another bridge, and my school is in that corner, the school from which I graduated, undergraduate. I like my name, I see it everywhere I go. It's amazing how many Freds there are in the world. Fred's God. And There's the Fred Society. There's Fred's Garage and Fred Min and the Fred Car. If found, please return. I tell people this is one of my students, but that's not true. I have no idea who that is. Okay. In Denmark, I used to walk past this building all the time, and this sign, Fred Og Forsonik and Kvinda Das Fred. And I thought, they certainly know how to make a visitor feel welcome. And I thought, before I put this up, I better make sure this is something I can share with other people. So I had to look online, and Danish Fred means peace, and this translates to peace and reconciliation. This is a sign I saw in Stockholm. I was teaching a class there once, and on the street signs, periodically this big sign said, "No Fred." I thought, how did they know I was coming? In Swedish, Fred is short for Fredag, and Fredag means Friday. So no Freds on Friday, that's what it says. This is my necktie closet, and I've got a couple of cartoon neckties, and some of them you may recognize, and some of them you may not. Sometimes, by a coincidence, one of the ties I'm wearing is one of the ties you can see, not at the moment. This is me at Halloween. That was Napoleon. I got that in England. I got Captain Cook in Australia. And the Palace Guard for the Wicked Witch of the West I got at the flea market in Spring Valley. And it's funny to walk into class dressed like this because the students want their picture taken to take it home, send home to their parents, say, "This is my teacher." And the parents get real worried about that, let me tell you. This is, every flat surface in my house has toys in it. I'm an avid toy collector. And these are trains. I bought that train in London and carried it home. There's a long story about that, which I won't bore you with. But I wanted to show this little license plate, and it wasn't a good picture. Now, this is in a little hallway in the house, but I happen to have its companion in my office, Mensch. And Mensch is Yiddish for being a good person. My mother kept on saying, "Be a Mensch, be a Mensch." So I had no choice. I had to be one. I have no idea what it is, but I'm one of those. This is my train room. And I have a little comment to make about this. Penny hyperventilates when she goes into this room, and when she leaves, she mumbles something about dust collectors. I have no idea what the dust collectors are, just dust everywhere. We do need a dust collector. She has the same response when she visits my office because it's similarly unorganized. This is a cartoon I found a long time ago. It hangs on my door. It says, "I'm very impressed the old man has his office piled with stacks and stacks of books on digital signal processing. He pretends they're mountains and he runs his electric trains around them." So I had to add this to this slide. Choo choo, chug 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 chug. That was Union Pacific. Tick 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 tick, a little train. She's supposed to be galloping. Sometimes she gallops, sometimes she doesn't. Okay. These are slides I got from a friend back in Boston, a guy named Don Steinbrecher. And we remind ourselves that whatever you told the customer that you were going to supply, this is what the customer heard. The customer heard more. More bandwidth, more bells, more whistles, more options, more wave shapes, more. And when Don gave me that, I realized there was something missing, so I had to add this to it. What does the customer expect to pay for more? And of course, the customer expects to pay less, even less. When I do this one in England, it has pound sterling. When I do it in Japan, it has yen, but here's the $ version. And when we expect to do more and more for less and less, we realize DSP is sort of the entry point to attack that set of problems. So that's what we do. We do digital signal processing. We're pretty good at it. Notice we're a little heartbeat there. In particular, we do DSP for communication systems, physical layer of radios, software-defined radios, and cognitive radios. These are two radios made by a company in Texas called Flex Radio. It's how it happens that the photograph was tilted in this direction. I had it tilted in this direction. You may not be able to read it, but I just reversed it so it faces the right direction. It now reads right to left. Where are we? This one has a funny story. Doing digital signal processing. There's a difference between working in the digital land versus analog land. In analog land, it's like working in Minnesota in high winter, snowing, cold air, harsh biting wind, no sunshine. On the other hand, digital land is like working in San Diego in high summer, gentle breezes, surfs up, That's because Eric's a surfer. Warm, sweet air, sunshine all the time. Well, I used to give this slide all the time when I was making presentations, as it says here. And one of the attendees presenting one of my talks said, "I'm offended by that slide. I live and work in Minnesota." So now, when I present the slide, I always make a comment. This is meant to be humorous. I mean no offense. Last Thursday, I was up in Irvine, and I had dinner with Minnesota Senator Amy Klobuchar and Congressman Eric Paulson. And I held my tongue and decided not to share the slide with them. I didn't think they would find humor in it. All right, this is what DSP looks like. The analog world enters the digital world through an A to D converter. We do things with clever algorithms and smart processors. We convert them back into the analog world through a D to A converter, and we then present an enhanced version of what it is with which we started. Now, the A to D and D to A are very important, so you should know what one of those are. And here's a description of what an A to D converter looks like. It's a machine where A's go in, something happens in the middle, and D's come out. And that's what an A to D converter does. Now, the neat thing about an A to D converter, it's reversible. You can put the D's in, and it does the opposite and spits out the A's. So we do transformations in both directions. This came out of a cartoon that was in the IEEE Los Angeles newspaper. I thought, I've got to use that somewhere. And when you find cartoons, you have to find an application for it. So here's one. It's all done with computer chips. This is a standard picture. Everyone has a version of this. It shows the timeline versus how many transistors you can put on a single chip. More, and this is Gordon Moore, who made an observation that the rate at which the density of transistors on a chip goes up, it's about a factor of an order of magnitude every 2 years. It doubles every 2 years. And if you follow from when he first made that observation of 4004, and Eric remembers when we dealt with 4004s, and now we're in the neighborhood where instead of having a couple of thousand chips, we now have 10 million chips. That's 10 billion chips. And that's remarkable how many transistors we can put in the system. And again, Gordon Moore, about 5 years ago, made an observation: we all own 1 billion transistors. An amazing source of wealth of what you can do with 1 billion transistors. And the thought was, I wonder how big 1 billion is. I have no concept. So we tried to make a reference out of it. 1 billion banknotes is a stack 76 kilometers high. 1 billion seconds from now, you'll be 32 years older. Now, here's a fun slide I've used, the Eiffel Tower. For comparison, the Eiffel Tower only has 18,000 parts in it. If you can do that with 18,000 parts, imagine what you can do with 1 billion parts. But this next little part is interesting. We recognize that as an exponential wave shape. We're electrical engineers, some of us. We know what an exponential is. So we're going to push that out of the way now and make this observation. Isn't that interesting? The shape that Eiffel built to build the Eiffel Tower, and he did it to basically absorb the wind loads, was an upside or standing up on the side exponential. He found out that if you use that wave shape, you don't need diagonal stresses or diagonal braces to absorb the wind load. The shape itself absorbs it without it. So those are only basically for looks rather than for actual structural value, the diagonal braces. He did it to reduce the weight. Okay. We know what silicon looks like. We know what rice looks like. And Gordon Moore made the comment that the world grows more transistors than it grows grains of rice. And we grow lots of grains of rice. Just walk around any rice field in India, China, or Japan. So it's quite remarkable. We do more of this than we do of that. So that made me think, I know what 1 billion transistors look like. It looks something like one of those chips. Wonder what 1 billion grains of rice look like. So it took me a little while to find out how big a grain of rice was. You can find anything online, but that's how big it is. 1 billion of them is a box that size, 8 meters by 2 meters by 2 meters. It's 3 meters on the side, weighs 24,000 kilograms. And when I checked the cost this morning on the rice market, 1 billion grains of rice would cost you $16,359. And that comes from $615 a ton. and the worst had to be about 31 cents a pound. And I thought, gee, if it's 31 cents a pound, I wonder what it costs in the supermarket. Well, a 12-pound bag costs $13. At 31 cents a pound, it should cost $4. There's a markup somewhere here. All right. So then my friend Don Steinbrecher asked, well, we know what 1 billion grains of rice costs. What does 1 billion transistors cost? Again, from Gordon Moore's presentation in 2003, he had this chart. In '68, a transistor cost $1, and as time goes forward, the price is going down. He stopped in 2002, so we have to go a little further. We're engineers, we know how to extrapolate. We go to the current time, we find 1 billion transistors cost about $20. Good price break. All right, what can you do with 1 billion transistors? This is a great little application. Sitting over Japan, there's a satellite beaming down 384 MP3 channels. They get demodulated and then remodulated on FM subcarriers to go into giant apartment houses. These old legacy systems are dying because they're old analog discretes, and the question was asked, if we replace the analog with digits, how big a room would it take to hold the digital version of the analog system? So there's the analog system. These are 19-inch racks. They're 6 feet tall. There are 12 on this side and 12 on this side. So the room, the equipment, the air conditioning, the lighting, all that's part of the cost of running this. So when asked, how big a room will it take? I said, I think it'll fit on a chip. And the response was, don't be absurd. You can't pack a room into a chip. Well, we certainly get close to it. That room is in that box, which is 2U high, 19 inches wide, and 12 inches deep. And that's not bad. So because I did it, we decided to write a paper. In fact, one of our students here, former students, we got 2 of them, are the other 2 authors here, Dragon and Wade. So we did this collectively, and we wrote a paper called How to Pack a Room into a Single Chip. We wrote that. That appeared in the Xilinx Xilinx newsletter or magazine. And about 6 months later, they sent us the Chinese version of what we wrote. The only thing that didn't get translated well was Fred Harris, Dragon Volotech, and Wade Loudermilk. And Xilinx doesn't trade, or FPGA. All right, so we're more than halfway there. Don't despair. We're going to get there soon. A short history of communications, because we need this to get to the back end. Why are we going to do what we're about to do? Early long-distance communication was free space optics or free space acoustics. Drums, whistles, telegraphs, fires, mirrors, ship's flags, something you could see over a long distance, but it had limited distance. So then we have a set of disruptive technologies, and the ones that are of interest to us is this leg of these 4, telegraph, telephone, wireless, and the microprocessor. Ted Hoff I met once in a patent infringement case when he had to describe what his qualifications were to be an expert in this case. He said, I invented a microprocessor. And I thought to myself, yeah, big deal. No one invented a microprocessor. But in fact, I did find out he is the inventor of the microprocessor. And he knew a lot about microprocessors, didn't know anything about communications. They had the wrong expert witness. Okay, and he was also charging more than I was. All right, here is a list. I don't want you to bore with the list. I just want to point to a couple of items. 1843, first telegraph. 1851, the company that became Western Union was formed. In 1861, the transcontinental telegraph was completed. You could send a telegraph from Boston to San Francisco. 2 days later, the Pony Express was disbanded. We don't need it anymore. We can get across the country in a short amount of time. But this is interesting. What the telegraph was used for, besides telegraphs, was ticker tape. And that is, we could send more information than just dits and dahs, Morse code. We could convert it into text and have the text written down somewhere. And that used to be called teletype when we did it then. Then it was telex, where telex was the main way we communicated long distance and kept a record of what the transactions were. That's 1962. And Western Union was actually a leader in technology for a while. In '74, they launched their own satellite, and in 2006, they stopped sending telegrams. You cannot send anyone a telegram anymore. It's sort of like records. Kids don't know what a record is. They don't know what a telegram is. They see it in movies. They'll never experience it. So since I mentioned the Pony Express, the Pony Express basically sent a horseman that traveled almost 2,000 miles, and to travel 2,000 miles took 10 and a half days. If you wanted to go by some other route, you could use the overland stagecoach and took 21 days. So it basically cut the trip in half. And I thought this ad was a funny ad. Wanted, young, skinny, wiry fellows, not over 18, must be an expert rider, willing to risk death daily, orphans preferred, wages $25 a week. Interesting job application. Interns, that's right. But that was interesting because at that time, $25 a week was a fortune because the average unskilled laborer was earning $1 a week at this time. And some very famous people were Pony Express riders. Buffalo Bill was one example. History and birth of modems. Basically, the world was connected by telegraphy. Telegraph wires made the world small. So when you wanted to communicate, your mechanism was over telegraph, teletype, teleprinters, telegraph, which were printing telegraphs. So when it came time to build other communication systems, when we wanted to put more communication out, we took that equipment and started putting them on telephone lines. So telephone lines became the substitute for telegraph lines. So in the early days of the Cold War, when we started putting air defense systems around Canada and Australia, we wanted to connect them all. We connected them with early modems, and they were called Sage modems, and they were modems that could operate 110 bauds. 110 baud is sub-audio. You can't even hear 110. So that was the first audio modems. And what a modem did historically, it connected machines through telephone wires to other machines. So basically, the telephone wire system was where we learned how to build modems. RF hadn't been thought of as an option. And if you plot as a function of time the data rate as we move data through telephone wires, in this period we went from mechanical modems to electrical modems. And when we went to electrical, then we went right through the sky. The technology that allowed us to build clever modems is this list, but the one that's the most important to us is adaptive equalizers. That is, the wires have bad channels, they attenuate the signal, you have to undo the distortion, and equalizer is needed. We're about to enter the RF world, and the RF world starts essentially with Marconi, and it advances quite rapidly between World War I and World War II. We had very well connected by radio broadcasting systems, but very seldom point-to-point. A comm system. We all took a course in comm. We know what it looks like. Bits arrive, they get converted to wave shapes go through the channel. The wave shapes are received, they're converted back into bits. The channel is modeled as having finite bandwidth and additive white Gaussian noise. And when you say additive white Gaussian noise, I worked as an electrician when I was in high school and college, and AWG was American wire gauge. It took me years to stop saying that. It's American wire gauge, here we are. Additive white Gaussian noise. So we talk about its amplitude distribution and its frequency distribution. Now, real channels aren't simply additive white Gaussian noise. That's what makes life interesting. You get non-uniform gain and phase. You get time-varying flat or frequency-dependent fading. You get non-uniform gain and power amplifiers. We get frequency offsets due to oscillator drift or velocity vectors, interference, and then we get noise. And the system has to work in spite of all of that. So I wrote a paper a couple of years ago in response to the fact that Wade and I were writing papers on synthetic instruments, and I kept on likening synthetic instruments to software-defined radios. And the question was, well, we know what a synthetic instrument is. Tell us what a software-defined radio is. And we wrote a paper. And I gave the menu for making modems. And in the menu, we have sort of three things you have to do. The first here is we must modulate and demodulate. The second tier is this one isn't going to work unless these others give you help, and the help is you must acquire frequency and phase synchronization, timing, frequency and phase synchronization, automatic gain control because the channel has disturbed the signal level, and you need a signal-to-noise ratio estimate. And you have little genies living in your radio helping you do these things. Then the third tier is because the analog world is imperfect, and you have to take out the tolerances and the mismatches, and we do that with equalizers and balancing circuits, and we control the distortion. And again, the one that seems important in this list is equalization. This has nothing to do except the fact Halloween is coming. So we had to acknowledge it. So this is what we think a modem looks like. We convert bits, and here are the list of bits, into wave shapes. And this is a frequency shift key modem. The sine waves go through a channel. They still look like sine waves coming out. Low frequency sine waves are different from high frequency sine waves. So what the demodulator does, it takes a derivative. Big signals, signals are made bigger if they're high frequency, bigger than if they're low frequency. You go through an envelope detector and you convert them back into ones and zeros. But in the real world, we have a real channel. And the channel is going to have limited bandwidth, so we have to build shaping filters which restrict the signal to the confinement of the available bandwidth. And we move them through the channel, and we do half the shaping on one side and half the shaping on the other. When you finish shaping, these are the observation points, which the timer genie says, make an observation now, and you get plus and minus 1 on the x-axis and plus and minus 1 on the y-axis. There's the simplest modem. Now, in the real world, the channel isn't just added to white Gaussian noise, it also distorts. And because it distorts, we know the shaping filter has a companion on this side called the match filter. The channel must have a companion on this side to undo the effect of the channel. We call that an equalizer. So this is what came out of the match filter after the channel distorted it, which doesn't look at all the way it's supposed to look. So the equalizer estimates the channel, constructs the inverse, undoes the distortion, and converts what we receive back to what we want. That's one option. Very, very simple. Again, the equalizer is going to be the driver in this presentation. So here's an example. The signal leaves the modem. Channel distorts it. The match filter tries to match the transmitter, but it doesn't do enough of a job to undo the channel. The equalizer undoes the channel. So we get two sets. GSM, best design I've ever seen. I have to give the French due acknowledgement. They said, here's our problem. We have a shaping filter and a channel. We have a match filter, but the match filter isn't matched to what we're receiving. So what GSM said is, let's probe the channel and find out what the channel impulse response is. We'll then take our estimate of the channel and put that in series with the match filter. Then we can think, this is what we meant to send you, and this is the match filter for what we did send you. Great little trick. So now we've got the match filter by adding a model of a channel to the receiver. But since we have a model of a channel, we can build a little system in here, and this little system tells you all the possible wave shapes you can receive. And that way you can use a Viterbi equalizer to trace through the trellis to keep track of the transitions between states. Brilliant, brilliant trick. Instead of treating the channel as something you have to get rid of, treat the channel as part of the solution, and then use a Viterbi equalizer, and this is the right place to talk about Viterbi equalizers, to undo the effect of the distortion. Great, great thing. And the reason they did that, manipulating waveforms is more expensive than manipulating bits. So if you move bits around in the equalizer, use less battery power. Great, great trick. All right, but other things happen to the signal. Here's an example where a signal gets passed through a rain cloud or a rainstorm, and you get attenuation. So the signal you send me is attenuated. That's flat fading. Here, a signal is finding two paths to get between transmitter and receiver. And of course, the two paths can add destructively. At a certain frequency, you wipe a hole in the spectrum. That really hurts, and even an equalizer can't fix that. So equalization finds there are limits to what it can do in a certain class of signals. If the equalizer is too difficult to address, change the class of signals. So when we talk about signal sets, there are three standard modulation forms. We have time versus frequency and how you're going to distribute energy. And what we can do, at a given time interval, we can use all the available bandwidth, and that's called time division multiple axis. On the other hand, at a given overtime, we can give you some fraction of the bandwidth, use that as long as you want, and that's called frequency division multiple axis. The third one is we can give you time and frequency all as long as you want it, but you have to be able to distinguish my user from another user by something called code division multiple axis. So we have multiple users, each one on our own time slot, multiple users, each one our own frequency band, and multiple users, each one separated by a code, which will then extract our code, leaving the rest behind. So here are a bunch of users. They all have different spreading functions. They go into the channel and each have a piece of the energy available. User number 1 is going to be decoded by someone who knows his sequence, spreading code. We despread an average, and lo and behold, our signal pops up, the rest gets suppressed, and we can extract any one of these from all the rest. This company existed because of that. All right, but if you get a very wide bandwidth system, you get significant multipath, and with a lot of multipath, even the CDMA isn't going to do well. Oh, this is CDM, I'm still here. So what the CDM equalizer looks like is this. We know that we have a bunch of paths, and each one has a certain amount of delay and a certain amount of gain. And what we can do is, because it's a wide bandwidth signal, we can build very narrow band, very narrow duration correlators and build a match filter for each of the multipaths. Then we align the multipaths, put the correct gain in so they're all phase coherent, and add them up, and it's called a rake receiver. Great little trick. So the ways we do equalizers are QAM, we build a tap delay line and invert the channel. GSM, we use a Viterbi decoder. CDMA, we build multiple correlators and combine the output of the correlators. But as the bandwidth goes up, these become impalatable. We invent a new waveform which gives us lower cost equalizers, and those are called frequency domain equalizers. Let me tell you what OFDM looks like. If you give me a certain bandwidth, I can fill the bandwidth up with one signal, a QAM signal. For instance, I have 6 megahertz bandwidth. I can do QAM at 6 meg and transmit a TV signal to you. Alternatively, I can take that same bandwidth and split it up into very narrow bands. And each of these narrow bands, because they're narrow band, have a long time duration. If they have a long time duration, the channel delays are insignificant. You can almost ignore them or easily avoid or correct the wave shape that have been properly delayed. I got this off Sharon Langston's webpage. I liked her idea. I didn't like her artwork, so I did my own artwork. And this is the other one I got from her webpage. In the QAM, you got a big truck delivering all the data at once. In OFDM, you got a whole bunch of little trucks delivering little pieces of data. If you get a flat tire, hardly matters, the rest of the trucks get through. So taking a lot of things and making them small is an interesting way to move data through a channel. So we have a narrow band channel, and we're going to build lots of them to occupy the full bandwidth. And the modulator is simply a Fourier transform. I put a signal in here, a sine wave comes out, and the sine wave occupies a given band. Put a sine wave in a different spot, it generates a sine wave, it's a different band. So I send you a bunch of sine waves. When the sine waves arrive, I ask a Fourier transform, tell me how big my sine waves are. You tell me how big they were, that's an estimate of how big they were at the input. The problem is we have a channel, and the channel is going to change not the shape of the sine waves, but the size of the sine waves. And so the size contains the information, you have to put the gain back in to undo the channel distortion. So what we do in OFDM, we send a probe through the channel and find the channel's frequency response. And we write it down somewhere, which says the channel has this spectrum response. Then we send data through, and we say, the signal that's arriving has the wrong gain. And I know what the gains are, so I'll invert each of the gains for each frequency, and I'll now have an equalizer, which is trivial. So this is data going through the system, and if I had no channel, this is the data I would see. These are all the amplitudes, 4 levels as a function of frequency. When you distort the signal, you don't do as well, but if you have an estimate of the channel, you can undo the effect of the channel. And here they are. 16 QAM, perfect channel. 16 QAM, an imperfect channel, and here it is, that red thing with the blue. We estimate the blue in the presence of noise, we invert the channel, and we get a flat spectrum within the tolerance or ability to measure the channel in the presence of additive noise. This is much better than that is in terms of keeping Euclidean distance between the collected data points. I got this curve from Gerhard Fettweiss at Dresden. Great picture. And what it is, it shows as a function of time, as we move forward in time, and the bandwidth and the modulation changed, we had to change from QAM to CDMA to OFDM because each of these had a different level of complexity to build the equalizer to undo the channel. So here are the lessons we learned. At very low data rates, we can use maximum likelihood sequence estimators, but that workload goes up exponentially with the length of the channel. The rake receiver, it only goes up linearly with the length of the channel. The channel gets longer, you put more rake fingers in. In OFDM, by using the Fourier transform, and we do the work in the frequency domain, the workload goes up only logarithmically with the channel. So notice the change from exponential to linear to logarithmic. It says if you want to go into high bandwidth systems, you must do logarithmic processing. You must do frequency domain equalizers. So now, we're going to show you how to do that. We have a few more minutes. Let's assume we have a signal which is going through a filter, and the filter is going to significantly reduce the bandwidth. This is where we get technical, and live with me for a minute. So if we're going to reduce the bandwidth, I have the option to lower the sampler rate. But in this application, we're not allowed to lower the sampler rate. In fact, I did that for a cubic design. They said, Fred, you have to keep the sampler rate the same. So we have ways of doing that. So it works out, we design a filter which will meet this specification. And what I want to do is lower the sampler rate because I think that's the right thing to do. You only have to have a sampler rate which exceeds the two-sided bandwidth. If you reduce the bandwidth by a factor of 50, you should lower the sampler rate by a factor of 50, which is what this does. But instead of lowering the sampler rate after the processing, we lower the sampler rate on the way in. So if you lower the sampler rate on the way in, you deliver 50 inputs, take an output, 50 inputs, take an output. Well, if you lower the sample rate before you do processing, you've aliased all the channels to baseband. And if you've aliased them, then you're in trouble. We go to a lot of trouble to avoid aliasing. That's the first thing we do, is we alias. Funny story. I once designed a modem for GTE, 64,000 channels aliased to baseband. And then we can unaliasing them with a clever trick. If you have 64,000 unknowns, you need 64,000 equations. It works out each of these rows is an equation. You have enough equations to undo the aliasing. When we got the review of our proposal back from the Navy, the review in big red letters across the front cover said, those people who don't understand the Nyquist theorem shouldn't be doing signal processing. And what I learned is if you're smarter than your reviewers, you're in trouble. Don't even try. So here's an example. I deliver 50 inputs, take an output, 50 inputs, take an output. But someone says, that's not acceptable, Fred. I need the input rate to be the same as the output rate. So I do this. I take my filter and I do the dual graph. And the dual graph says, if I deliver 50 inputs, take out an output, the dual graph says, give me one input and I'll give you back 50 outputs. Now, why is that better? Well, the original filter had 400 taps. So 400 taps would cost me 400 multiplies and adds per input-output pair. But now what happens, each of these little arms is only 1/50 of the filter. They're 8-tap filters. So 8 taps get multiplied and add. And of course, data comes out at 1/50 of the rate. And I then raise the rate. And every time I take an output sample, it costs me 8 multiplies and adds. Every time you give me an input sample, it's 8 multiplies and adds. So input to output, it's only 16 operations instead of 400. Why would someone do 400 operations at the clock rate when you can do 8 operations at the input, 8 at the output? It says if you want to keep the same sampler rate, that's a different problem than the one which is let's reduce the bandwidth. You reduce the bandwidth and lower the sampler rate. Then you build a second filter to give you back the sampler rate you wanted. And if you treat them as two problems, even though it looks like you're doing more work, you're actually doing significantly less work. 16 out of 400, what does that work out to be? That's 1/25 of the work, only 4% of the work to get the same work done. It's foolish not to do this. In fact, it's criminal not to do this. So here's the original design, 400 in, 400 multiplies and add per input-output pair, 8 operations per input, 8 operations per output, much less hardware. 400 addresses here, only 16 addresses here. So this is what you want to do in multi-rate signal processing. If I put both of these in a box and say they both do the same thing, 20 meg in, 20 meg out, they reduce the bandwidth, how do you know which is inside the box? It's called the wet finger test. Go. And the wet finger test is you touch it. Ouch. Ooh. It took me half an hour to find a pretty hand to do this one. They're all there, you just have to find them. So here's the problem. We just learned this is a better way to solve the problem. I have a big bunch of bandwidth. I want a little hunk of it taken out. So you design the filter, and because you have more bandwidth, more sample rate than you need, you lower the sample rate. What you get out of this is the bandwidth you want at a reduced sample rate. Then you build a dual graph, and it says, I'll take that same bandwidth and raise the sample rate. And I've just saved money in doing that. Not only do you save money there, but you save money elsewhere. Instead of building a low-pass filter, I want to build a bandpass filter. And we know how to build bandpass filters. So what you do, you put rotators in the filter. All these signals alias to baseband. All these guys have gone to baseband, and what the spinners do, they extract this alias. So that alias is now DC. Then you bring the sample rate up, and you put these spinners on, and the spinners put the data back where it wanted to go. And again, what happened, if there are 8 multiplies and adds per input and 8 multiplies per output, there's an additional 2 multiplies here and 2 multiplies here. So now I built the system now, instead of 16, it's 20 multiplies and adds, instead of the heterodyne and the 400 tap filters. The 400 tap filter would be 1 on I and 1 on Q. Here there's only 1 filter. Already I've saved half the work. 1 filter is going to service both I and Q instead of 2. What's interesting, I've done a design like this. I can alias the signal of interest down to baseband, and then I can alias the signal up to a different center frequency from which it came. These set of rotators can be different than those set of rotators. So I can extract this band and put it in another band at the same time, at the same cost, and you hardly even notice that happened. Well, what if I want to get more than one band out? Remember, what makes this a bandpass filter is not the filters, it's the rotators. If I want to get another channel out, all I need is another set of rotators here, another set of rotators here, but I don't change the filters. So here I have another plane, the blue plane, and the blue plane is another set of rotators. He now rotates the data back up, so I got 2 outputs, one of them from the black, one from the blue, and I put the spinners, and I add the 2 paths together and put them in the filter, and I get 2 frequencies that have been down converted and up converted for essentially the same 2 filters. All it's cost me is a set of rotators. Now, let's see this little comment. If I want 1 filter, I need M rotators. 2 filters, I need 2 M rotators. If I want M channels, I need M of those rotators. But suppose M is a big number, like a Fourier transform. Well, the number of rotators, instead of being M times the length of the filter, in a transform, it's log M over 2 times M. So when the number of filters you want is bigger than log M over 2, this is what you do. You build all the filters and throw away the ones you don't want. For instance, suppose I need 5 filters. So I could build 5 sets of rotators. But I could build a 128-point transform, and the cost of doing a 128-point transform is only 3.5 times the cost of building 1 filter. So if I need 5 of them, I'll build all 128 and throw away 123, and I still save money. Channelizers are so inexpensive, it's cheaper to build them all and discard the ones not of interest to you. You need that information, that channelizers are dirt cheap. So if we need a lot of rotators, we put them in an FFT. So this is what our system looks like, our polyphase filter, and the rotators to pick out any of the alias channels at baseband is simply an IFFT, and I can get a signal out of DC, the one at the first nyquist zone, the second nyquist zone, they're all available. And Dilbert likes that idea. But now when we design the filters come out of that polyphase filter. What we're going to do is not build a standard channelizer, but a very special channelizer. A channelizer where the filters are Nyquist filters. The electrical engineers know what I'm talking about. The Nyquist filter has 3 dB down at the edge. If you go through the filter twice, you get is a square root Nyquist. Then you get a Nyquist filter, and you get perfect reconstruction if you add this path to this path to this path. And that perfect reconstruction is magic. We learned a long time ago, you can go into the frequency domain, modify the spectrum, come back into the time domain, that's called fast convolution. The problem is the block process. You give me M inputs, I'll give you M outputs, and there are boundaries because I turn the data on and turn it off. And we always have to fix the boundaries with something called overlap and add and overlap and save. This is the engineering part, bear with me. So this is what we're going to do. Instead of having a Fourier transform by itself, we're going to build one of these polyphase filters. And the polyphase filter doesn't have a boundary condition. Data flows into it continuously. You give it blocks of M at a time, but the M keeps on recirculating. So data flows in continuously. You take the transform. You then modify the spectrum, do the inverse transform, and come back into the time domain. Well, notice what happens. If I want to build a filter, I can leave off certain paths. If I don't want these channels to contribute to the output, you build a mask. The mask is 1 or 0. If you set it to 0, you just lost that part of the spectrum. So this is what you might see. I had, in this case, 120 bands, and I engaged 25 of them, and the ones I didn't use, of course, have no output. So this is the impulse response to that system we just described. And this is, I allowed more of them to come through, so I've opened up the bandwidth. But notice, this is actually a pretty small amount of work, and I'll show you why. I start with the 600 tap filter. I build 120 paths, so there are 5 multiplies here and 5 multiplies here. The fact there are 2 is not important now. We build the transform, so it costs me 10 multiplies per input. It works out a 120-point transform, takes about 300 multiplies. If you split it over the 50 inputs you deliver, it's about 2.5 multiplies per input if you amortize it. Same thing coming out. So between input and output, I have 10 plus 2.5 plus 2.5 plus 10 is 25 multiplies per input-output pair. Just the way that little low-pass filter was. Now it's a full bandwidth. The direct convolution with 600 multiplies. This, what looks like an amazing amount of extra work, is only 25 multiplies. That's only 4% of the work. You discard 96% of the work if you're willing to build a polyphase filter, build a Fourier transform, another polyphase filter, and it now gives you the filtering you had up there with only 5% of the work. You have to be clever in the program. We're clever. The more interesting part about this is if I want to change the bandwidth of the filter, I need a new set of coefficients up there. To change the bandwidth of this filter, I change the mask. And the mask is 1s and 0s. So now I have a variable bandwidth filter, which hardly costs me anything. And now it says, do the demo. So we have a little bit more than the demo. Don't despair. We're almost home. And the demo is in MATLAB. Love MATLAB. It's waiting to run. And there it is. So there's the system I just described. And what I'm doing, I'm turning on and off the masking of the coefficients between the input transform and the output transform. And notice we have filtering down to about 110 dB. And it's only costing me about 25 multiplies and adds per output point to build a 600 tap filter. Had I built the 600 tap filter, it would have cost me 600 multiplies and adds per input output point. If you don't think this is impressive, you're a hard audience, that's all I can say. All right. Now, this is where the clever comes in, and then we're finished. You always sort of call attention to the change. All right, we can do interesting things. This is the system I described. The Fourier transform, we have a mask. The inverse transform, we rebuild the signal. Well, if we only take a few of these frequencies out, we don't need the high sample rate anymore. And the rule is if you're reducing bandwidth, reduce sample rate. So we bring in the data at the full sampler rate, we pick the bandwidth that we want to preserve, and we pass out a transform which matches the amount of data we want to move out. So we reduce the size of the transform, and now we still have that same efficiency, but even more efficient. Well, we can take out multiple channels. We can have one band of frequencies be assembled, another band of frequencies, some of them without additional partition. And now we have the option to build a channelizer which can service multiple simultaneous different bandwidth signals out of the same channelizer. So here's an example where these fat channels are going through my channelizer, and I broke it up in little pieces. Skinny channel, he successfully goes through. A fat and a medium fat don't get out. The fat one is broken in little pieces. The middle one is broken in pieces. The skinny one actually gets out. But I can take these, which are 3 adjacent frequency bands, and when they're 3 adjacent frequency bands, I can put them in a little reconstruction system and build the output built from those frequency bands. And here they are. We have rebuilt the signals that didn't need any extra construction. Here we use 3 adjacent channels, and here we use 6 adjacent channels. And what we put in comes out exactly with no distortion. It's perfect reconstruction, because those are Nyquist filters in the process. If you give me a bunch of signals which have different bandwidth and ask me to build a modulator, the modulator expects only a certain fixed bandwidth, and you gave me different bandwidths, no problem. The dual graph is you take the signal, break it up into these little narrow bands, and then these little narrow bands are reassembled in the synthesizer. So here's, for instance, is the fat channel. And the fat channel goes through the analysis and says, well, I need this little piece and this piece, this one, this one. And I take those 5 and deliver them to 5 input ports in the next system. And here are the pieces that we're putting in. And of course, what comes out is when I take these pieces, I can put them anywhere I want. So that's how we shift them to different frequency bands. So I get coarse frequency location by simply moving to the right address. And what I move depends upon how many points we move in. The more points, the wider the bandwidth we move across. Almost at the end. Now, because we can move them, we can be cavalier. I can rearrange their order. Just because they came in this order doesn't mean I have to take them out in that order. So here's a system where red represents the bandwidth of each channelizer, 120 channels. I gave a medium-sized channel, a great big fat channel, a bunch of little ones. And what I did is I took the signals that came out of here and moved them over. Some of these I moved over, some of them I left alone, and this guy I moved over. So you can, for free, get the channelization, rearrange the spectrum any way you want. And the last one is, suppose I have any signal that you can think of. I can break it up into little channels, and now my equalizer says, well, each of these channels has a gain and phase. As it went through the channel, I can correct the gain and phase and reassemble the output. So we can modify the spectrum between input and output with the inverse of the channel, which we've obtained by some probe. And now we have, for arbitrary input spectra, a frequency domain equalizer whose cost is only n log n, or only log n, just the way it is in OFDM. And that's it. Software defined radio man, almost, pretty good. You may recognize the big S for software. And there's the guy who wears the big S. You may recognize is open for questions. There we are. So that's my closing slide, except for this one. Now, open for questions. So that's all I had to say. If you have an interest in this kind of work, come see us at San Diego State. If you have money you want to throw at graduate students, come see us at San Diego State. If you have money you want to use to support faculty or our graduate students, any combination, we're certainly interested in talking to you. Open for questions. It's bad when people are nodding and not agreeing with you, it means they're going to sleep. When they're not responding, that means they've gone to sleep. Yes?
Hold on. Move some of your energies around to different areas in the spectrum. What's the advantage of doing that? What do you gain from moving a large bandwidth to some other area in your...
A lot of service providers do that. A service provider has contracted to take a band of frequencies he's received and transmit them in another band of frequencies. That's common in contracting. And normally what he does, he down converts them to baseband, he shifts them over and then up converts them, but I don't have to do that. The same channelizer will do that for me all at once. Pardon me? It's a bent pipe, but I can move it from one frequency to another. Or we can rearrange them. It could be that in my contract, 6 of these go out of one band and 6 go out of another band, but they all came in as adjacent bands. So he has great flexibility. There are other things you can do besides these in a limited time. I don't want to bore you with all the possibilities. But the equalizer is a great one. The equalizer is will be the driver in the next generation. When we go not to 100 megabit data rate, but a gigabit data rate, the only way you're going to fight the channel is this way. There's nothing else that'll do it. This is the key to the next generation of modems. I actually have one more slide. Okay. I mentioned my wife. I bring home all these little, this is a radio, this is a wind-up toy, this is a little vibrating toy that we put these out for the cats. The cats don't like that at all. And then these are things I just found on the web, which will spook someone. So, any other questions? Yes, Ron? Sure. Another application is I have a cognitive radio, and the cognitive radio is given a task. Here, radio, here's a megahertz worth of bandwidth. Go find an empty spot and launch it into the ether. And the cognitive radio has kept track of the local spectrum and says, I can't find a gap. I can't find a megahertz worth of bandwidth, but I've got 100K here, 200K here, and 400K here. He can take those little pieces, partition them, give each little piece, and then by telling the other side, hey, I've partitioned the signal, reassemble the signal, because we've gone around occupiers that we weren't allowed to interfere with. That's an example of what you can do in a cognitive radio. It's that classic joke you see where you see tracks of someone skiing, they come to a tree, and the tracks went around the tree, and how'd they do that? Well, they had one of these little channelizers. So that's one example. Yes? Well, we've done a couple of theses on this. In fact, I did one 2 days ago, which was a channelizer that did white space detection. And once you declare that you found the white space, then the cognitive radio says, all right, I've got the band, I'm not allowed to put it in these adjacent bands. It works out. The channelizer that does spectrum analysis and the channelizer that does the modulation is the same channelizer. It's the same piece of hardware. So you can be running a spectrum analyzer in the background while you're doing your modulation as a foreground task. Anyone else? That's it. Thank you for coming. It's 8 o'clock, and that's pretty, it's not 8 o'clock, it's 7 o'clock. 7 o'clock. And again, I would like to thank you for coming here. I'd like to thank Peggy and Eric for hosting us all. And I would like to thank the dean, who would probably like to say something now. He's the one of the two copies we have. I don't know which one.
Thanks so much. It's been great. You just said everything I was supposed to say, which is thank you.
Okay.
I just want to spend just a second saying first, thank you, Fred. I just enjoyed the passion here. Now you have to understand, over the last couple of weeks, people in the college have been coming up to me and saying, is this a lecture I can understand? So I kept asking Fred. He goes, absolutely, absolutely. Fred, sometimes you exaggerate.
I sometimes do. I didn't want to disappoint the technologist amongst us.
I will have to answer to some folks tomorrow for that.
Okay.
I also want to thank Qualcomm for providing this venue for this great lecture, and especially for Eric and Peggy Johnson for their unrelenting support of our College of Engineering. I just mentioned Fred's passion for this technology. They have equal passion for the university, and we very much appreciate their efforts and the efforts to support our wireless communication program at San Diego State. So Eric and Peggy, thank you so much for everything. That's it.
Thank you. That's it.